Hi there, this is Matt Heffernan, and welcome back to the Retro Desk. Today we're going to be taking another look at the Agon Light, which is this new microcomputer based on the eZ80 microcontroller, and it is, of course, a platform for using BBC Basic, but of course a lot more. You can use the eZ80 in assembly language, you can program it in C, and there's a lot of different ways of being able to get this modern 8-bit computer to do all sorts of interesting things. So today we're going to put it through its paces, do the full hello world on it, and see how that's going to work. So first, a bit of a word about BBC Basic. Well, what is that? Well, BBC Basic was created by Sophie Wilson for Acorn Electronics, so way back when the British Broadcasting Corporation, the main broadcaster that's publicly owned in the United Kingdom, wanted to promote computer literacy and wanted to get schools to have these simple microcomputers. Maybe not so simple. In fact, they were far more advanced than most other microcomputers at the time. But of course, more simple than a professional computer, which would have been like a big mainframe computer at that time. And so Acorn had to come up with a basic interpreter for it, as that was pretty much what most microcomputers are doing. Of course, they were also mostly using Microsoft's version of that. And Acorn's design for the BBC Micro also used a 6502, but rather than going into a licensing deal with Microsoft, they just had Sophie create it for them. And so there it is, a completely new 6502 basic interpreter. And that was on all of the BBC micros, as well as the non-BBC branded Acorn 8-bit computers that were also based on the 6502, like the Acorn Electron, and eventually other computers started using it too. Now, the reason it works on the Agon is because it was ported to the Z80 by R.T. Russell. Well, who's he? Well, he's a guy that actually worked at the BBC, and he was one of those source selectors for Acorn, saying that, hey, Acorn looks like they know what they're doing. They have a good idea of how to get a microcomputer up and running. Of course, if you've watched the dramatization of that in the British TV movie Micromen, that was sort of a slap together thing that they managed to make work at the last minute. And but it was good enough to get the contract for the BBC. Russell signed off on it and was then inspired to create his own. And it ended up on things like the Amstrad CPC and a bunch of other Z80 based computers at the time back in the 80s. So it's been around for a long time, and it has since been open sourced. And so now we can use it on things like the Agon. What Dean Belfield did, he is the main software guy that is creating this environment for programming the Agon. He made it work with the Agon using Russell's code. And of course, he's been sharing this on his blog. That's called Break Into Program. That's his general identity online, is Break Into Program. And he, of course, also wrote the MOS and VDP firmwares that run on the Agon. And we're going to be learning a bit more about that. But first, we need to see BBC Basic in action. So, of course, here on the Agon, we just have a basic prompt. And like with literally any other basic interpreter, you can just start writing a program right at the prompt. And so we'll give it line number 10, because what else are we going to do? And we're going to say print. Of course, I have to be in all caps for the Agon for all these basic commands, but I can take the caps lock off and do a nicely formatted in mixed case string to print out. And there we go. There's my Hello World program. So if I just run it, I can't be in lowercase. I got to go back to caps, run it, and there it is. Hello World. Simple as that. That's the whole reason why we like these 8-bit computers. So how does this actually happen on the Agon? Well, it's not as simple as it was with the BBC Micro. There is other microcomputers from the 70s and 80s that you may be familiar with. This, of course, is a very modern take on how to create a microcomputer using current technologies. Before we go any further, I want to say a little word about our sponsor, PCBWay. Now, you know them as a company that makes these really high quality printed circuit boards for all sorts of projects and even for some industrial prototyping. It's not just small things, they can be big things as well. And one of the projects that started on PCBWay is the Agon, and specifically the Agon Light. And this here is PCBWay Plus, where you can buy still the original Agon Light, not the Agon Light 2 that you've seen on my channel from Olimex. This is the one that was done by the creator through PCBWay, and it has a few differences from the Agon Light 2. This one can actually take a real PS2 keyboard directly. It does not have that USB port like the Olimex version. So there's a few small changes, but it's software compatible. But there are many other projects on there that you can buy completely built. And going forward, once this sells out, you will always be able to build your own Agon Light if you so desired, because the board itself is something that you can order manufactured for yourself, and it already has a listed bill of materials that you can then procure also directly from PCBWay, and you can have them assemble it. So really, PCBWay is a one-stop shop, not just at the prototyping stage, but through manufacturing and distribution. They can get it to anybody worldwide, and you can use either the local currency like I have here. I could buy this with $103 cash. It is more expensive, but this is a limited quantity item. Or I could use beans if I acquired enough beans from doing other purchases through PCBWay. I could buy it from my bean inventory. So it's a really great place to go, get your project made, explore what other people are doing, and create custom PCBs, and also do all the machining, 3D printing, CNC fabrication, and the population of those PCBs. It's all there for you at PCBWay.com. And now let's get back to programming the Agon in some more different ways. So let's take a look at the actual architecture of the Agon Light. As you can see here, there's a lot of different components, but most of this is actually I/O, and almost all of it is wrapped up inside these two microcontrollers. Let's first with what we're calling the CPU, which is the eZ80. And that's, of course, the main executive processor that exists on the Agon. And most of the software that you're going to run for that is running specifically on the eZ80. And in fact, everything that we're going to be doing in this video is for creating software to run on here. But as we've seen before with things like the TT-Go VGA32, the ESP32 itself is an extremely capable processor. It can do a whole lot. And as you can see, this version here is running at 240 megahertz compared to the 18 megahertz that the eZ80 is running at. So yeah, there's a bit of a power imbalance here where the more powerful processor is not the one actually doing all of the general processing. Here we are using the ESP32 and all that speed and everything to control the VGA signal, control the audio output, and do the things like run the PS2 port for the keyboard. So it's already doing a lot, and it's pretty much only able to communicate with that main CPU over this serial link. It's like a megabit serial link. And so everything that we want to do from BBC Basic or from any other eZ80 based program, it's only going to access any audio and video through that link. And even the keyboard, all those keyboard commands are going to have to go up that link to the CPU. So it ends up being kind of a bottleneck within this architecture. And really, if you just took that side of the ESP32 with those ports and its built-in memory, and then this USB port down here that we can program it on, it's pretty much just like any other ESP32 development board, like the TT Go. And in theory, you could just use it as such. It's got the 8 megabyte version. A lot of those demos that we saw on the VGA32 would very likely run on here, no problem. But that's generally not what people are buying this for. They're buying it for having that BBC Basic and being able to use that Z80 version that's running on there. So what we're not going to do is do a hello world for this particular subsystem, at least not in this video. Now, I may do a later video where I create a FabGL version of hello world and have that run on this and the TT Go as both being ESP32 FabGL development boards. The other thing that we're not going to use for programming is the ZDI port. Now, this is a proprietary interface by Zilog for programming the internal flash memory of the eZ80. And it also has built-in RAM. It's really very self-contained. But as you can see here, we have this additional SRAM that's on there. It's 512K of SRAM that's on a separate chip. And we also have a micro SD card. And so that is what we're going to be programming on. Of course, we've already seen the PS2 port for just typing stuff in to BASIC, but we'll be able to even store either from BASIC, be able to save off those programs from BASIC, or take that micro SD card, put that in a modern computer, and be able to load that up with cross-developed software for the eZ80. And it'll pop into back into the Agon and be able to run on the eZ80 off of that card port. But if you did want to run something off the flash that's built into the eZ80, you got to use that ZDI port, and you have to use the proprietary cable for that. And that ends up being even more expensive than the Agon itself. It's like $100 if you want to get that whole Zilog development kit. And so basically what we get with the Agon are sort of two development boards that are put on the same PCB with the serial link between them, so that the eZ80 side works pretty much like any eZ80 development board like you would get from Zilog, and then this ESP32 part, which is very similar to something like the TT Go, except it doesn't have things like Wi-Fi and Bluetooth built into it. This is a much smaller, lower cost ESP32. In fact, the ESP32 is extremely low cost, much lower cost than the eZ80. And it's even though it is technically a more powerful CPU, it has a much wider set of use cases and is produced at much higher quantities. So that's where we're at with this system, this strange two-headed beast. And we're going to go a little deeper now into the different ways that you can program it. And to really understand that, we have to take a look at the software ecosystem that is running within here. So for software, we got a few different things. We've talked about the difference between the firmware and the software on there. The first piece of firmware is called VDP, and that is a FabGL audio-video keyboard adapter that, of course, runs on that ESP32 subsystem. And it's written in the Arduino programming language. And if you've seen that before, like in my TT Go video, the Arduino language is very C++ like language. In this case, it is using FabGL, just like those other demos that we saw, but to specifically answer to commands that are going to come over that serial link from the eZ80 side, as well as push things up. Specifically, those keyboard events are going to get pushed up as serial data packets back to the eZ80 side. And on the eZ80 itself, we have MOS burnt into the internal flash of that. And it's a very simple operating system for dealing with the file system on the micro SD card and handling that additional I/O, specifically the SPI that micro SD card connection is on, and there also has an I2C controller as well, and of course the serial connection, which is part of the eZ80. This firmware is written in a combination of C and assembly language, and it runs right on that eZ80, and it actually uses eZ80 assembly language, and that's an important distinction, as we'll see. And by coming on the built-in flash, it's not something that has to be loaded over that SPI connection to the micro SD card. It can boot up pretty much instantly from MOS, and then what it's doing mainly is using that built-in UART that is in the eZ80 to send what are called VDU commands to that ESP32 side, and that's what VDP will be responding to, and that's how it does all the video and the audio and everything. So that's pretty much what MOS is doing, and MOS provides an API to any assembly language program, C program, and even the basic interpreter itself. But of course, like I said, as we've seen, most people are going to be using BBC Basic. And that BBC Basic is just a Z80 assembly language program. Of course, it's because it was written back in the 80s. It's not eZ80. And it has to run on top of MOS, and that's what Dean's version effectively does. Takes Russell's version and makes it run on MOS, and then it's able to do all of those VDU commands and also be loaded from the micro SD card. That is not actually burnt into the flash. So if you do not have a flash card mounted and inserted into your Agon, you're just going to get the plain MOS prompt. And we're going to see what that looks like pretty soon, because you don't have to be running BASIC all the time. You can drop down directly into MOS and run other non-BASIC applications from that. So let's talk a bit about what this distinction is with eZ80 assembly language, because we've seen on my channel all the stuff for learning how to program Z80, specifically for the Sinclair ZX Spectrum. What makes the eZ80 different? Well, it has a special mode called ADL, stands for address and data long. And what this means is that the eZ80 is capable of running with a 24-bit address bus as opposed to the 16-bit address bus that the legacy Z80 has. And so then the registers for dealing with addresses are further expanded to have these 24-bit values. They have an extra 8 bits to all of those registers that you can then put in this, whatever you want to call it, a bank, a super page. What the Zilog terminology is a memory base or M base. And that's what you need to be able to set, is say, okay, we are going to be from this 8-bit base of memory, and that's going to give us this, the remaining 16 bits of the address are going to be within that 64K segment of RAM, or whatever kind of memory you're dealing with. Now, the MOS API, all it basically does is provide some restart vectors. And we've seen restart vectors before with the ZX Spectrum. And we've used a lot of them, like The hex 10 restart vector we used for sending characters into the display, and guess what? It does the same thing on the Agon Light, and then it has a few others that you're going to want to use once you get deeper into how to do assembly programming with Agon. Obviously, you don't want to reset it a whole lot, but it is a single instruction to just reset it. And then there is the restart 8, which will execute these different MOS commands for dealing mainly with the file system. And then hex 10 will be putting out one character at a time, and 18 will be a string at a time. And there is you can define a delimiter for the end of that string. It can be null, but it could be another character too. And that string could just be text that is getting printed to what is effectively a built-in terminal, but then you could also have control characters within that string, and then that will change what's actually happening. It's not just printing text anymore. It is then doing perhaps some sound or some graphics or whatever works within that VDU interface. And that's going to be the topic of a later video. We're not going to get into all that. All we're going to care about right now is just printing text, because we're just doing a hello world. And so that restart 18 will do everything we need. And in order to actually build these assembly language program, we have eZ80 ASM, and this is an open source assembler. You can use the Zilog assembler also, but if you want to have something that is going to be a little more flexible, eZ80 ASM can run anywhere. I'm running it on Linux here, and you can even run it on the Agon. We're going to see in both cases how we can do that. So let's take a look at what this is going to entail. And another bit of warning before we see the code, there is going to be a lot of extra window dressing to make it look like an application for running within MOS. And so let's see what I mean by that right now. And so here it is. This is the assembly language version of Hello World. And it's a little wordier than we might have thought it was going to be, but that's that window dressing. And so we're going to break down all of these different things that need to happen in assembly language in order to get what we need to create a simple MOS application. And it would be a little more balanced with a more involved application. The window dressing is not going to take up the majority of the program in those cases. So first, let's take a look at our first line of code here. Now, this is not actual machine code. This is a directive, an assume directive, and it's going to say, hey, when this program starts running, we're going to assume that the processor is already in ADL mode. And that is a valid assumption, that if you drop down to MOS, that's where you're going to be. And then, like in pretty much any assembler, it takes .org statements to say where in memory is this program going to start. And here we're going to say at 04 as the sort of base of the memory, and then right at the beginning of that. So you can see already we're using these 24-bit addresses because we are in ADL mode. And then the very first thing we're going to do is jump to the start label. And in between, we're going to have this header. And needs to be aligned to 64 bytes, and it needs to have the string MOS in ASCII, and then a 0 followed by a 1. In each of those are, of course, going to be single bytes that we'll see within this header. And then after that header, we can start. So MOS is going to just look for that to say, hey, yeah, this is something that's safe for me to run. it should be an executable intended for the Agon to run on top of MOS. Now, before we start doing anything, we want to sort of preserve our state. So we're just going to push all these registers up. And it's not strictly necessary, but it is a nice thing to do. And I could get rid of this in there and it would probably still run just fine. But this just, it makes things nice and safe and makes sure that after this runs, we can cleanly return back to the MOS prompt without going off into outer space. And then here we start the actual meat of the program. Now we need to load the address of our string into the HL register. And of course, we can see our string is down here. That string just has hello world, and then it follows that visible text with some control characters, the standard carriage return and line feed, and then is null terminated. And so that's what that's going to point to. And of course, we are in ADL mode. So this is going to be loading into the special 24-bit version of HL with this 24-bit address for hello string. And then we're going to be doing the same thing here with the BC register. We're going to be loading that here in ADL mode, but with a 0. And that is going to say, hey, when BC is 0, that means that we aren't reading a fixed number of bytes from that address. We're going to wait until we hit the delimiter. And then that delimiter gets put into the A register, and we're going to specify that as a null character or a 0 byte. Once we see a 0 byte in that string, we are going to stop reading that out of memory. And then to start pumping that byte stream into the VDP over that serial connection, we're going to do restart. Now you notice this is a little different than our standard restart. We don't just say restart hex 18. We have a restart.lil. This is going to make sure that we are using the version of the restart, the opcode, that will assume that we are in ADL mode. And so we're going to have a 24-bit return address. And it is going to then be going into code that is also in ADL mode. And that's what the LIL stands for. So it's long going into long. And so then when we return from that, we're all done. We'll have had that whole string up through that null terminator, pumped into that VDP, the VDP program running on the ESP32 subsystem. And then we can just pop all our registers back off. And then to be extra nice, we want to reset HL to 0. We don't need to preserve what HL was before that. MOS just likes to see HL at 0. So we will oblige that, and then we return. And that, in this state, should get us back to the MOS prompt, and everything is hunky-dory. Now, to build this, we're going to use, like we've mentioned before, eZ80 assembler. So it is quite simply just eZ80 ASM, and it's hello.asm is the that source, and we're going to give it a -L so that it generates a program listing, so we can take a look at what the machine code actually looks like when we do that. And so you can see it does a 2-pass assembly job, and it's done. So let's take a look at that listing. What does this actually come up with? So some of the things we were expecting is that, yep, it's going to obey this org directive, so that we are starting at at the 04 segment of memory, which for the Agon is the beginning of that user space RAM. Going up to that point is what MOS is going to be using. And then we have here our jump. And boy, that looks awfully big for a absolute jump instruction. Yeah, it's actually takes up 4 bytes because we are in ADL mode. And that assumption, by when we assumed ADL, it's like, all right, well, if we're going to jump, then we're going to be using start as a 24-bit address. So that's what we get here. Is it's 040045 is start, and we can see down here, there it is. There's the start at that address. So this ADL version of jump is going to be 4 bytes long. So as you can see, it is, even though we're running a lot faster, we're running at 18 megahertz on the eZ80, a lot of that time is going to get sucked up by dealing with these longer instructions. So yeah, it's not all all just going whiz bang fast, but some of that, of course, will be improved because then to execute these instructions after the fetch, it's a lot more efficient than the original eZ80, or the original Z80, not the eZ80. And of course, in between, we can see that 64 align gave us a bunch of zeros leading up to MOS, and being aligned at 64 meant that here at 40 hex is where we're going to start that MOS string, and then we're going to be all good. Everything is nice and neatly placed where it needs to be. But then a lot of the other instructions we can see are just as we would expect to see them in a regular Z80. So all of these are exactly the same. But here again, we see ADL versions of loading into what are in Z80 land 16-bit registers, but now they are 24-bit registers. So when we're loading addresses or just a scalar value into them, they are 24-bit values. So a 24-bit address going into HL, a 24-bit integer going into BC, but then, of course, the accumulator itself, the A register, is still just 8 bits. So no matter what, we can load things into there very quickly. And then here we see this long going into long version of restart 18. And unlike the original restarts in ADL mode, we do require 2-byte opcode for this. It's no longer a single byte opcode. And so again, a little bit of extra fetching that needs to happen. But then we're back to our normally scheduled Z80 style instructions, and then here we are loading a 24-bit integer version of 0 into HL. But then returning is the same old single byte opcode, and there we have it. And of course, here we can see our full string in there with all of the ASCII characters. And that is a nice thing, is that it just uses standard ASCII. It doesn't use some weird encoding here. And then we have at the end our carriage return, line feed, and the null terminator, all clearly there. So let's take a look now at how this would run. So what we get for an output is this hello.bin file. You can see here right in the middle of the listing. And that is the executable. That's the binary version of that listing we just saw. So we can transfer that to a micro SD card, and just pop that in the Agon, and now we can watch it run. All right, so back on the Agon. Of course, we are still in BASIC. We've run the basic version of Hello World. Now, to get back to MOS, we begin with a star. A star is our escape within the BBC Basic to send in an MOS command, so we don't need to be in all caps anymore, and we can just say bye. And now we just have the asterisk for our prompt. And that says that, hey, we're now in MOS. We're no longer in this sort of old-fashioned basic world, and we can just run things. And so we can do MOS commands, which are very similar to a lot of other simple OSs like DOS or CPM, or even early versions of Unix to change directories. We do a CD. And what we'd want to do is to get out of the directory we're in, which is a special directory for the BBC Basic test examples that you're going to get on there. And we'll look into how a lot of that works. So we're going to go up a directory and into a directory you create on here called hello. And then we can do a dir, just like we would on DOS or CPM. And so now we can see the hello.bin that we built on the Linux PC, and here it is. So let's go ahead and load and run it. And so to do that on MOS, we do a load just like we do on BASIC. We don't need the quotes though. We can just say load hello.bin and then run it. And there it is, hello world. Very simple. Now, what we can do is actually do this assembly directly on the Agon. So you can see I've also copied that ASM, that source code right on here. And there's a bunch of utilities that are out there. We've already talked about eZ80 ASM. We've seen the Linux version. And so the Agon version, of course, just runs right here on the Agon on MOS as an MOS application. And so you can add that to the MOS directory on your SD card, and it'll run it like that. Another thing you can add on there is a version of Nano. So let's take a look at that source code in Nano. So I can do nano hello.asm. Now it switches to this different screen mode. You can see here we're in a nice 80-column screen mode now. And we can see that same exact code. We don't have to change it at all. We have the same assembler running right here. So I'll exit out of Nano, and I use the same command, eZ80 ASM hello.asm, and I'll again ask for the listing with a -l, of course, and now it's not working. And that's because it's not called eZ80 ASM on here. I think I just have it called ASM. And so ASM hello.asm and -l. So that's the only difference. It's the same assembler, and you can see even the same output as we saw on Linux. It runs a little slower, but we're dealing with a much slower computer here. And what this has created is that it's recreated hello.bin. Now you can see the date's a little funny on it. The real-time clock is not quite set up correctly on the Agon. That's something that needs a little work on here. But what you can do is you can take a look at that listing file now. We did just regenerate that hello.list. And you can see it's the same listing file that we saw before on Linux. So it's, you don't have to change the source code at all. If you want to do your development right in Nano on the Agon or whatever text editor you want to put on there, you can do that. You want to do cross development, you have that flexibility. So that's a really nice feature. And all of this was just sort of put together by the community. This isn't something that comes with MOS to get the assembler and Nano and all that. These are different folks within the community that are coming up with this. So that's the really the nice thing about this project is that everything about it is open source, and people from all over the community are contributing these important things that are starting to help make this platform a bit more mature. It still has a long way to go before it's up there with some of these other modern 8-bit style computers, but it's definitely has some great community support right now, and we're able to see all of these different things happening. So I go out of Nano, I'm back here, and I can now run load up again hello.bin and run it, and there it is. It's still running exactly the same as the version that I had compiled on my modern fancy computer. So now, what do we do about somebody who doesn't want to do basic, because basic is just kind of infuriating to deal with if you're not just some beginner just playing around. And assembly language, it can be, it's a big mountain to climb, especially now when we're talking about the eZ80, and we've got to deal with a machine that can go between two different kinds of addressing modes. It starts to get a little unwieldy. So this is where we look to C. Of course, we've done C on the Commander X16, and that used the CC65 toolset. Now we don't have something quite that sophisticated yet for the Agon, but what we do have is SDCC, which is the Small Device C Compiler. And this is mainly targeted at modern small microcontrollers like the eZ80, and be able to have an extremely simple C compiler that can make it easy to have your code be split up between assembly and C, and just to do some a very light amount of C on there. It has a ways to go, but what it does let us do, it gets us back into cross development. It does not run currently on the Agon. That's not to say that a C compiler couldn't run on there. I say it certainly could. It would be a little slow. Compiling C code is a lot more labor intensive than just doing assembly. Yeah, it's not going to be that quick couple of seconds that we saw with assembling that Hello World. It's going to take a bit more doing to do on this old-fashioned system. What we can do with SDCC is have all of these different small CPUs, microcontrollers, and things supported, and we can include the eZ80 on that, but only by virtue of the fact that it's backwards compatible with the Z80. So any C code that we write for the Agon, it's not going to be eZ80 machine code coming out. It's not going to be ADL mode. It is going to have to be in regular old-fashioned Z80 machine code and not be able to take advantage of 24-bit addressing. And another big hole in there is the fact that we don't have full implementation of the C libraries, the standard C things like standard IO, standard lib, all of those nice things we expect with any given C compiler, like we have with CC65. We have all of those things implemented for all of these different platforms that are supported. You don't get that with SDCC, especially not for Z80, because it doesn't really target specific Z80 platforms on there. It's just like, well, here, this will This will generate Z80 code, and that's about it. So in order to get SDCC to use say the standard IO library, we want to have put care and get care implemented. And so thankfully the community has done that because, of course, as we've seen, doing any sort of keyboard action or printing to the screen requires interfacing with VDP over that serial connection. So that's what the put care and get care do for this extra code that we have to put in there. So let's take a look now at what that is. So let's go into hello.c. Now, this should look blazingly familiar to pretty much anybody out there. This is your bog standard hello.c that should, any sort of platform that supports C should be able to do this. Just do printf hello world and then put your end line encoded at the end. And in this case, we're using the DOS Windows style line ending of carriage return and line feed. Super easy. There it is. So now how does this translate into Z80 code that we can actually run on the Agon? Well, it's going to require a few extra bits. So here we can see this assembly language header that is required on there. This it's a library that is going to deal with MOS. And here we can see the put care and the get care, where it's using those restart vectors here to that restart 10 to print out a specific character that is getting printed to the terminal. And this is using that put care prototype that is within the standard sort of front end of the standard IO library that is built into the SDCC. It just sort of has a gaping hole of, well, how do you actually put a character in there? We can get you this far. Just show me how to do that. And the same thing with the get car. You can see here it's doing the MOS command for doing that, and that is achieved by putting a 0 into the accumulator. And that's what that exclusive OR. Doing exclusive OR of A is the fastest way on a Z80 to just 0 out the accumulator. That's sort of an old trick, and it works pretty well here. And then we can see here, then we get that result in the A register, but get care is going to need it in the L register, and from there the rest of the library can handle it. So we need to have this code linked in with our RC code. And then we can see here there's some header files that are expected. So yeah, common.h is going to say, all right, I need to type def unsigned car and unsigned int because we don't know what those are for this platform. And then a header file called mos.h that's just going to include that common. So yeah, just some basic things that are required in there. And then here we're going to have another module that is needed for creating that MOS header on there. So just like we had put into the assembly language version, this will help put that in there too. Although it sort of does it a little different. I'm not fully clear on how all of this was decided again on, but we can see the window dressing that was implemented for this sort of simple minimal C application on the Agon. Somebody came up with all this. I'll have links to all that, but of course it's in my repo right here, just so that we can simply get this hello.c to work. And so to do that, we go back to the terminal. We can go into that SDCC directory. that I have there. And if we take a look in there, there is a make file, and within that make file is going to do all the things that we need. All we have to do is have SDCC installed in the path, and so there's all the magic incantations that are required, and then gets all wrapped up nicely into a single bin file. And if we take a look, that bin file is actually pretty small. It's only 237 bytes. It manages to to cram right in there. So it's a very, very tight C compiler when you're using this extremely simple version of the standard IO library that just does, put char, get char. Doesn't handle any of the file IO, so we don't get all of that extra fluff that we're not going to need in the Hello World application. So, all right, let's now go back to the Agon and we'll take a look at how this runs. All right, so of course we had just run this program that was written in assembly language, and if we do a dir, we can see we created an SDCC directory on here. So we have just sort of copied all that stuff that we created on Linux into there. And so I'm going to go into SDCC, and in there we'll see that hello.bin that we created. And you can see it's not much bigger than the one we assembled. And we can see the hello.c. So just because we can take a look at hello.c in Nano, and there it is, just as we would expect it to be. And we can also look at the listing file. We'll actually look at the listing file right here in on the Agon. So let's take a look at that listing file of what we're getting. So here you can see it's a lot more stuff that gets put into the listing file. It definitely looks very different from the listing file that we saw from eZ80 assembler. But we can see everything that it's doing in hello.c. To do a printf, it's doing a call to a put string, just as we would expect. It's optimized enough to know that, hey, I'm doing a printf, but I'm not actually putting any extra arguments in there. I'm not trying to insert anything into that string. And so it just says, all right, well, we're just printing a string, so we'll just call puts and be done with it. We don't have to do any sort of formatting or parsing of what's in that string that's been passed to printf. And so, yeah, it makes it very, very tight. So this is a pretty good, pretty smart C compiler, at least when we're dealing with an extremely simple example like this. And of course, this is only showing what the C code looks like. It doesn't have the full listing of that binary, but it would, in that case, you would see all of the window dressing in there, and we'd see that additional code that was written for the MOS API. So now we go back to our MOS, and like in the other cases, we've called it hello.bin. So again, we're going to load hello.bin, and we're going to run. And there it is, hello world. So now we've seen all the different ways of being able to program the Agon. And this is just through sort of normal means, without any special equipment and without actually getting into overriding any of the firmware that's on there. And of course, those are additional ways of being able to program it. You don't have to use MOS. You don't have to use the VDP. You could use each of them as sort of their own development packages for that. You can use it as a eZ80 development board. You could use it as an ESP32 development board. However you want to actually approach the Agon, you can do that. But sticking with the standard firmware, this is how it goes. All right. I hope you enjoyed this. And if you want to see me do some more stuff on the Agon, anything specifically, go ahead and put that down in the comments. And if you want to see when that comes out, best thing to do is subscribe to the channel and click that bell to be notified so that you'll see as soon as I post any new content. But the best thing you can do, of course, is become a part of our Patreon community. Like the folks you see here, they really help make this channel run, and they get to see videos like this ad-free. You're not going to be bothered by that sponsor back there in the middle, and you're not going to see any other ads in there in a non-monetized version of this video that you'll be able to see forever and ever by being one of those kind patrons. All right. So until I see you next time, take care. Bye bye.